Okay, here we go. This is take one on Eric's ghetto classroom setup here. All right. So we have a ball or any object neglecting air resistance is thrown, let's say, horizontally, perfectly horizontally with respect to gravity. Has some mass m. We're going to say that it's h, distance h off the ground, and it's going to come down in some parabolic shape with respect to x being distance t. And so hypothetically, we don't know how long it takes. We might not know how tall it was, how high it was, or the distance. So let's take a look at this from a variable point of view, I guess, just to define some things. So at time equals 0, we are here. The ball has some velocity vector, which has only an x component, and at time 0, the initial value of velocity of x is some capital V. I'm just going to define that with a variable. We also know that at initial time, the y component of the velocity equals 0. Okay. Again, horizontal. Also in here is we're on the Earth, and so we have force of gravity, which again is perpendicular to the initial direction y, or velocity vector. Okay, so it's going to come down, and in our final conditions, we're going to have some final x component of the velocity, and we have some final y component of the velocity. Now, this term is now non-zero because it's been accelerating at the gravitational rate of whatever units you like, some distance per unit time squared, and has some final velocity. Okay, so we thank Newton for his second law, which was basically conservation of momentum. Okay, and so he said that the only way you can change the momentum, which is mass times velocity of mass, is to apply some force to it over some amount of time. So in this, we're going to say that mass is constant. The ball is not like ablating away as it's falling through the atmosphere like an asteroid might, for example. We're going to look here in terms of vector notation. So there's some force vector on m, so F on m, and there's a resulting velocity vector, V. Okay, so Cartesian coordinates, we're talking x in two dimensions. Out of this vector equation, we're going to get two equations because there's two dimensions. Let's further reduce this a little bit here to equation 1. So again, mass is constant, so if you take the derivative of this term, mass is not a function of time, and so that term comes out of the derivative, and we're left with the derivative of the velocity vector with respect to time equals the force vector. Okay, so let's look at the x component of this equation, so x direction, I guess. So from our vectors, we have the force in the x direction on the ball is equal to the mass times the time rate of change of the velocity in the x direction. So we've gone from vectors now to scalars, because everything is, we're only looking at magnitudes in one direction, and so we can do this by, so now we get rid of our vectors. Now we know from our assumptions, and what we're told is that once at time 0, the ball, let's say, leaves our hand, or a bullet leaves a gun barrel, or a cannonball leaves the cannon barrel. There's no other force once it has been given this initial velocity, okay? And so the force is 0, and so this side is also equal to 0. Because mass times this term equals 0, we don't assume that the trivial solution is that this is 0. So we can basically divide each side by mass, and we get rid of mass. And we're left with d vx dt. So again, time rate of change of the velocity in the x direction with time. So this is a function of time. I'm going to jack this up. Okay, equals 0. Or another way to say it is the derivative of the velocity in the x with respect to time equals 0. All right, so we can do some calculus here. Now my math isn't going to be totally consistent through here. Anyway, but we'll keep going here. So we have a derivative, okay? So now we're going to integrate with respect to time, okay? And so an integral is like the area under something, under a curve, if you will. So we're going to look at the total change effect over this time in this integral, okay? And we're going to integrate both sides of the equation to keep it equal. So the integral with respect to time of dv dt is just v plus some constant, if we're talking indefinite integral. Integral of 0 is 0, so that's still 0. So I'm treating it now as an indefinite integral, and you may or may not know what that is, but because we're not defining the bounds, we have some constant that we don't necessarily know. However, in this case we do, because we know that at time equals 0, again, this case right here, we know that the velocity, we know that the velocity versus time is equal to some constant. So, whether you can move this over the other side of the equation, and it's still constant. We know that that's constant. And we've defined that actually is this capital V. Okay, so indefinite integral of dv dt with respect to time, we simply get that the velocity is some constant, which we are given that, or we're trying to find that actually. So that's cool, which basically says that Vx initial value is equal to the Vx final value, again is equal to V. Now we can't really do a whole lot with that, other than just show what we've already assumed. So now we also know that the velocity of x in the x direction with respect to time is equal to the change in x with the change of time. So so we differentiate x versus time, we get the velocity, distance over time, and we know that that's equal to the capital V. Okay, so what do we do with this now? Well, we now take the integral of this term. And I'm syncing here. Okay. So we're going to take the integral of both sides. Again, integral dx dt with respect to time equals the integral of the constant time with respect to time. Now I'm switching over to a definite integral here. This essentially, these cancel in a way, and you get this dx, and then you evaluate it from the final minus the initial value of x. So definite integral, you can take a look at definite integral versus indefinite integral on Wikipedia or something, but conceptually it's almost like you're canceling out your dt's and you're left with dx. And so what does dx mean? It means it's the difference between the final value and the initial value. Okay, so we know that just from how we've defined our coordinate system here. So x, we're saying that the x value at initial time is 0. So that term drops out, and so we have just our final x position, which, I'll jump ahead a little bit, is in fact the d value, which we're after, equals the other side of this equation. Now, the other side of the equation, so we were integrating the constant v with respect to time. Now, if you look at an integral table, that the integral of a constant is equal to that constant times whatever that times that value, your I guess dependent variable. So now we actually have a term for t in here. Okay, so now we know that the capital V times t equals d. If we solve for that, this will be useful later. But again, this is sort of, you know, the long way to get to what you might just find in your textbook, or the simple equation is that distance equals velocity times time. So the distance that it goes has nothing to do with the mass, and it will go out it'll keep going out until it hits something that'll stop it, okay, after some amount of time. So all that we get out of the x component of the vector version of the second law of motion simply is that it's going to go distance d, and it's going to take some amount of time. Okay, again, so we'll call that equation 2. Now let's go to the y component of equation 1 again, which was the vector form of the momentum balance, or conservation of momentum, I should say. Let's see. So I think you can maybe jump back and see it. So now we have, so the forces in the sum of the forces in the y are going to equal the mass, same mass, times the time rate of change of the y component of the velocity with respect to time. This we know, or we've assumed and are told that the only forces that are acting on it are in fact gravity, and so this is equal to the force of gravity, which we also know from Newton is equal to the mass. Oops, my finger is getting tired. Is equal to the mass times that gravitational constant. So if we now kind of look at these two pieces of the equation, these are still equal here. The mass drops out, and so we're left basically with g equals dv dt. So again, there's no mass dependence here, so it doesn't matter how much mass it is under this gravitational constant, it's going to take a certain amount of time, or it's going to reach a certain velocity after a certain amount of time. Again, that's the analogy of, you know, dropping a golf ball versus a bowling ball. Neglecting air resistance, they are, if they drop from the same height, now they're obviously different sizes, so you have to account for that, but they're going to hit the ground at the same time because it doesn't matter what the mass is, it turns out. They're going to at least have the same velocity, and so since the same distance, they're going to have the same time. Okay, so we integrate a constant because they're not falling far enough where g actually changes. The integral of a constant, again, is simply whatever that dependent variable is, t. We assume that time 0 equals 0, so we're not going to carry that through. So basically, I have g times total time is the integral of this. And again, so I'm jumping back to an indefinite integral, is vy, which is a function of time, plus some constant again. The way we find our constant is we look at our initial condition, or final condition, but we happen to know our initial condition, which is when t equals 0, so this term goes away at time equals 0. The velocity in the y is 0, and so we can then solve here for c2. In fact, c2 equals 0. If you do this for the definite integral, you basically get your initial velocity and your final velocity terms, which of course you also know that initial velocity is 0, so you get the same answer. This is anyway, indefinite integral approach. Okay, so we know C2 is 0, so we come back to this equation, and now we have the velocity in the y is equal to g times t, which in itself is, you know, is a solution that we may be interested. But if we wanted to know what that velocity was, but we're not really interested in that, we want to know, we're given information about the height, and so that's kind of a clue. We're going to need to get towards actual displacement or motion in the y direction. And so once again, same way we did with the x component, was that, you know, we basically ended up with Vx was a constant, and we said that was dx dt. In the case in the y direction, we're basically doing the same thing. Where are we here? We are saying that the velocity in the y is equal to dy dt. Now, instead of being a constant like it was in the x direction, this is the y component, and we know that y is not constant. I'm sorry, the velocity is not constant, it's a function of time, so it's the g times t. So we have this equation, gt equals dy dt. Again, this is a differential. We get rid of the differential by integrating, and so this is a little hard to see, but this is the integral of gt with respect to time is equal to the integral of dy dt with respect to time. Now let's see, this is the cool part here. Well, not cool, slightly more interesting than it was. G is a constant, and so that comes out. But now we have a dependent variable in here. So the integral of t dt, you can look it up in the integral table, is just by definition is 1/2 t squared. So that's just that's a mathematical statement. There's no other physics involved there. It's a mathematical statement. or mathematical truth, whatever you want to call it. You can in fact differentiate this term and you get back to t. So you can go from the integral of t goes to 1/2 t squared. You differentiate 1/2 t squared and you go back to t. So that's how differentials and integrals work. So anyway, you have this cool 1/2 term, and now I have a t squared term on the left. On the right, we're going to handle our dy dt integral now with a definite integral, because we do know the terms here. The definition of basically of some variable that's a function of time with respect to time is the initial value minus the final value. So this is the y value at when the ball hits the ground minus the y value when it started. Okay, and so in fact the final value is 0 based on our definition. So we said that x equals 0, or no, y equals 0 at the bottom, and it started out with an h height and it fell down. So this is h. So now we'll gather our terms together. We have g 1/2 t squared is equal to just minus h now in this case. So we have equation 3. If we look back up here, equation 2, we have d over v equals t. We just need to know two of the, well, yeah. So we have 1, 2, 3 variables here. If we look at this equation, we have 1, 2, 3. T is common here, so we actually have 3. We know g, so we have like 4 variables with 2 equations. So we need to be given 2 values. So we either need to know time and h, or we need to know h and d, or we need to know d and v, or v and t. You get the idea. So we have to be given 2 of these 4 values to be able to solve this. But let's just say they gave us the height, and they also gave us this initial velocity, which is anyway common. We combine equations 2 and 3 by substituting the time into this equation. So we're going to solve this by substitution. So we have g 1/2. Now we have the d over v, all of that squared. That's our time term, minus or equals the minus h. So we want to know d out of what's left here. We know everything else. So we know the initial velocity, we knew the height, we know what g is. So we'll solve for d, and you manipulate this around and you get the square root of minus 2h over g times v. So the v, let's see, yeah, the v is not in the square root here. This is my little equation box. So is our solution. So we know this, we know this, we know this. You can solve that to give up to d, and then once you know the d, then substitute that back in equation 2, and you can solve for t. So again, we have our 2 equations we got from the x and the y components of the single vector momentum or momentum conservation equation. So that's that. And so what I did, I don't know, just a visual thing here. Oops, that's all my other garbage. So I just I just made a little spreadsheet because I love spreadsheets, because I'm a visual person. So I assumed that let's see, I'm gonna try to make this bigger for the moment. Okay, so I assume that we knew H, so we have a ball, throwing it, and it's a meter off the ground. G, now, so you may have been concerned about how do you take the square root of a negative number that's an imaginary number, but don't worry, because G, the way we've defined our coordinate system, so y is positive going up. This gravity vector is actually down, and so the magnitude of it is negative. And so this actually becomes a positive term, which lets you take the square root of it. And I'm going to just say that horizontal velocity is 2 meters per second. Just as an example, and I have a touch screen, so that happened. So then I just made a little table. I just said time, and I said incremented time by 1/10 of a second. And then I calculated x. So again, basically the x and the y motion are separate from each other. What's happening in the x direction is defined by this equation, that the distance is equal to the time times the velocity, right? And so that's what we've done in here. Basically just saying time times velocity is going to give me my distance. The y term, now this is again the vertical term. Okay, come on, buttons. There we go. This is, now if we look at our so H is basically, this is our vertical component, but it's basically this G 1/2 t squared is the y value. So y, again, 1/2 G times time squared plus H is this initial value, is the y. Now if I just calculate these over a range of time, and I can you can see this is just plotting these coordinates, that y is going down, or I'm sorry, the ball position is going down versus time. So each of these is a different time step, and it's moving out in the x direction. So you can see again so the velocity in the x is constant, so each time step we get the same displacement in the x direction. So these intervals are equal if you look at just dx. So dx dt is constant for each of these because, again, constant velocity. Now if you look at dy dt, you can see that dy is getting larger for each of the same time steps. So dy dt is not constant, it's equal to g, okay, basically. So the ball gets farther away from where it was each time. So anyway, this shows you the trajectory. These equations right here, so right in here, I put in the equations that we got from the derivation. So for d, and then so d equals t times v, and then let's see, now I must have used this equation right here to independently solve for them. And so I just, again, I plug in random numbers here, and so I get d equals 0.9 meters and time is like 0.45 seconds. So we can look on our plot here, and you can see that in fact when y gets to 0, it's somewhere around in here. X is somewhere right around about 0.9, which you can is our solution. So that is the run through of the horizontal ball throwing. Hopefully that made sense. One thing, you know, there's obviously several variations. Now this is getting all shaky here. Several variations, of course, you know, that you can be given parameters, but in the end, you might know D, you might know H, what was the velocity, or the time of flight you might be given. So I mean, the problems depends on what you're given. Another variation could be, well, what if this is, let's say it's a rocket. It's not a ball, it's a rocket. So it has its own propellant, and so it's got a force. And let's just say that rocket thrust on the rocket is constant force. And so a variation on this would be when we look at the X term, that in fact the Fx is not 0, it's some thrust value. And so when we go through and solve this, rather than getting this sort of trivial solution of d over v equals t, we're going to have the rocket, the thrust force in here. And so again, that would just carry through the derivation same way, but we would have this would be non-zero, and so when we integrate, we're gonna gather some a t value here. That's force, the thrust force times time, and so in the end, why do I keep losing my, rather than in this case, each of these time intervals, we have the same distance. These are going to get farther apart in the x direction. Now, even if this is a rocket with thrust, it's still going to hit the ground at the same, it's going to hit the ground the same time if you just dropped it. Now this curve gets way elongated out here because now it's going, maybe tens of meters per second instead of a meter per second here. And so, the distance obviously is much longer because the time of flight was longer, but it would theoretically still be the same amount of time if you simply just drop the rocket and let it hit the ground. So again, another point about it's the equations of motion are they're independent of each other. It's really looking at your coordinate system. Now, this is Cartesian coordinates. Again, we looked at both coordinate systems. If you're just dropping a ball with no motion, you would only have one term or one equation. You would have this, your y equation here, okay, and this gets a little bit simpler now. I have to think about that, but you don't have a y, you don't have an x component basically in that case. That's obviously. The other thing, of course, is if you have drag force, you don't have a constant F value here. The drag force is actually a function of velocity, and so as the velocity goes up, the force goes up. And so a more advanced problem here of dropping a ball is dropping a ball with drag, and you will find one, you have to know, of course, that relationship between the force of drag and velocity, but that basically gets plugged into this equation. And so now instead of let's see, you know, we ended up with only a G term here. You still have your force term, and now you're integrating that force term, and so this gets much more complicated, but it's the same approach. You would simply have your drag force divided by G, because the mass would still fall out here. Actually, no, you have two terms. You're going to have your gravity force minus your drag force. Okay, one is a function of mass, or I'm sorry, one is a function of G. The other one is just a function of velocity. So it gets more complicated in the end, but it's the same kind of approach. Alrighty, hope that helped. I love you, and have a good night, day, whatever.